Hey everyone, and welcome. Today, we're going to decode the invisible grid that wraps around our entire planet. You know, the system that powers everything from your car's navigation to global time zones. So let's dive into the amazing world of latitude and longitude.
I mean, have you ever really stopped to think about it? You type an address into your phone, and boom, a little blue dot instantly knows exactly where you are and where you need to go. How in the world is that even possible on this massive spinning sphere we call home?
Well, that's the fundamental challenge, right? The sheer scale of our world. I mean, you can't just point and say, it's over there. That just doesn't cut it. We needed a precise mathematical way to describe any and every single point on the surface.
And the solution, believe it or not, was cooked up by ancient thinkers. Let's take a look at how they did it.
The solution is called the geographic grid. The easiest way to think about it is to imagine a giant, invisible net draped over the entire planet. You've got these east to west lines and north to south lines crisscrossing, and at every single one of those intersections, we get a unique, precise address for any spot on Earth.
At its core, the whole concept is surprisingly simple. I want you to think all the way back to math class with that classic graph paper. Well, this grid works the exact same way as an X and Y axis. One set of lines tells you how far up or down you are, and the other tells you how far left or right. Simple as that.
And you know, this isn't some new high-tech idea. We're talking about the Greek philosopher Eratosthenes, the guy who first calculated the circumference of the Earth. He was already working with a system of latitude and longitude over 2,000 years ago. Just incredible. Okay, so let's break this grid down piece by piece. We'll start with the first part of our grid, latitude, which is all about defining our vertical position on the map. So what is latitude? Well, at its heart, it's just an angle. It measures in degrees how far north or south a place is from one single starting line, the equator, which sits right at 0 degrees. These lines are also called parallels, and for a good reason. They run parallel to the equator, and they never ever touch. Now, there are a few key parallels here you've probably heard of. We start with the equator at 0 degrees, of course. Then, as we move out, we hit the tropics of Cancer and Capricorn. And finally, the Arctic and Antarctic circles, which take us all the way to the poles at 90 degrees north and 90 degrees south. But okay, why do we even care about latitude? What's it actually good for? Well, it turns out it has 3 really critical jobs. First, it pinpoints our north-south location. Second, it helps us measure distance. Each degree is roughly 111 kilometers. And third, and this is a big one, it divides the entire Earth into distinct climate zones. That's right, your latitude basically determines your climate. The area squished between the tropics is the torrid zone. That's the hot one. Then, the areas between the tropics and the polar circles are the temperate zones, where you get more moderate climates. And beyond that, you've got the cold, frigid zones right at the poles. Now that we've got our north-south position locked in, let's look at the other half of the grid, longitude. And here's the cool part. To really understand longitude, you have to understand its deep, deep connection to time. So longitude is the angular distance of a place east or west of its starting line, which is the prime meridian, running straight through Greenwich in London. Now, unlike the parallels of latitude, these lines, called meridians, actually all meet up at the poles. You know, the link between longitude and time is actually baked right into the word itself. The word meridian comes from the Latin word for noon. And why is that? Because every single place located on the exact same line of longitude experiences noon at the exact same moment. And we can calculate this connection with some pretty simple math. The Earth rotates 360 degrees in 24 hours. If you break that down, it means it spins 1 degree every 4 minutes. So for every single degree of longitude you travel, the local time changes by exactly 4 minutes. It's like clockwork. So we have latitude for our north-south position and for climate, and we have longitude for our east-west position and for time. Now let's see how they work together. Let's do a quick side-by-side to really lock in the key differences. Latitude lines, remember, are those parallel circles that get smaller as they get closer to the poles, and we use them for location and climate. Longitude lines, on the other hand, are all equal-length semicircles that meet at the poles, and they are absolutely crucial for location and for time zones. Okay, let's put that 4-minute rule into practice. Say you need to find the time in Montreal when it's 5:30 p.m. in India. It sounds complicated, but it's really not. Step 1, find the difference in their longitudes.
Step 2, multiply that number by 4 to get the time difference in minutes. Step 3, just convert that to hours. And finally, you just need to add or subtract depending on which way you're going. And to make that last step super simple and completely foolproof, there's a handy little mnemonic, EGWLS. If the place is to the east, you gain time, so you add. If it's to the west, you lose time, so you subtract. It's a really effective way to remember. All right, for our final piece of the puzzle, let's look at a pro-level application of this grid. It's a global travel trick for finding the absolute shortest path between any 2 points on the globe. This involves something called a great circle. Just imagine a circle that slices the Earth into 2 perfectly equal halves. That's a great circle. The equator is a perfect example. And here's the key takeaway. The path along the arc of a great circle is always the shortest route between 2 points. And this is exactly why flight paths on a flat map can look so strange. A flight from New York to Moscow, for instance, doesn't just fly in a straight line across the map. It actually curves way up over Greenland near the North Pole. That curve looks longer, but it's part of a great circle, and it actually makes the journey thousands of kilometers shorter. So this isn't just some fun geometry puzzle. Navigators for ships and planes live by these great circle routes to save a ton of fuel and time, and even meteorologists use these same paths to help model global weather patterns. So there you have it, an ancient system of invisible lines that literally organizes our entire planet. The next time that little blue dot pops up on your screen, I want you to take a second and actually picture the grid. Can you feel those lines of latitude and longitude intersecting to pinpoint your exact place in this world?